For the demonstration that I'd like to conduct for you today, I have 3 overhead projectors set up. I just wanted to show you that there are 3, because in a moment you're not going to see them at all. I also have color gels that, that I can place on them. This is a green gel, this is a red gel, and the gel's sort of just a piece of transparent material that only allows a very narrow wavelength range to pass through. This one only really allows red light through. So when placed on a white overhead transparency, only red is broadcast. So in a sense, it's a way to create pure red light. But as it relates to color, I can't tell you how many times I've heard art folks, painters, people who work with physical media to make art, say that the primary colors are yellow, blue, and I guess they say red oftentimes. And they'll say yellow and blue make green. That's true if you're using crayons or paint, but it is not true about light. And fundamentally, what we talk about in physics is light. There have been some thin film interference problems where they say sunlight falls on a film of gasoline, and because of the elimination of green light, the film appears magenta. And I thought to myself as I was leaving our last class that, you know, many of you have never seen colors mixed properly, or the last time you saw it was at the Exploratorium when you were, you know, younger than a teenager. So I'm going to perform some color mixing, but I want to just get back to this issue about people who do art and work with color, and physics types who work with light. Pigments absorb. They are chemicals whose structure allows them to selectively absorb some wavelengths of light and reflect others. That which is absorbed is removed. So pigments add in a subtractive way. So they perform a subtraction of light. And I'm wearing a white shirt for a reason today. And I may talk about that a little bit. Or you may just see me in the light and notice that my shirt takes on colors. White light is truly the presence of all colors. And to simplify, we say there is red, green, and blue. Now, of course, there are more colors than that compose white light. If you take a prism and you, as Newton did, and you put sunlight into it, you get a rainbow: red, orange, yellow, green, blue, indigo, violet. To simplify it, we just take what we call the 3 primary colors: red, green, and blue. If you mix all 3 primary colors, you get white, okay? If you mix 2 of the primary colors, you get what we call a secondary color. Red and green together, any guesses? Because you're going to see it in a minute, and it's surprising. Red and green together make yellow. Yellow is what your brain perceives when the red cones in your eye, you have 3 color cone cells in your eye: red cones, green cones, and blue cones, if you're born with normal color vision. And when the red cones and the green cones fire in your neural optical nerve simultaneously, that perception you've learned to call yellow, and it's a color. If you take red and green, green and blue together, the color we get, it's called cyan. It's kind of like the color of a deep swimming pool, bluish green. No surprise there. And if you mix red and blue, you get magenta. I'd like to show you that now. Again, when you mix color, when you mix light, not when you mix paints or flow pens or anything that removes some frequency. We're going to add light rather than subtract it. So here's red. And here's blue. And here's a deep blue. Together, red and blue make magenta. Red and green again, I think this always surprises people, make yellow. Red light, and green light make yellow light. Now, something I'd like to emphasize here is that when you're adding light, think about it. As a kid, when you mix paints all together, if you kept going, eventually you got brown or black. Because the more pigment you add, the more subtraction you're doing, and ultimately you end up with black, which is the absence of all light. When we mix two primary colors, red and green in this case, what we get is lighter. Yellow is a lighter color than either red or green, right? So, because what are we mixing? Light. We're mixing light. I'm wearing white, so if I put my white shirt in the red light, white is capable of reflecting all light. That's why white clothes are cool in summertime, because they reflect a lot of the light that strikes on them. So if I put it in only red light, it can only reflect red light. If I put it only in green light, it can only the only light striking it is green, so it appears green. And if I put it in the yellow light, it appears yellow. It's reflecting both green and red, which is, again, your eye's perception of yellow. The other fun one, of course, is cyan, which I'm going to mix with blue and green, and we get this lighter color again. A lighter color because there's more light. I'm trying not to keep emphasizing that. But it's worth thinking about it that way because it's different than pigments. Let's add in red. And so now we have the three primary colors, red, green, and blue. Here only the blue and green overlap. We have cyan. Here only the red and the blue overlap, and we have magenta. But here we have white. And you might look at it and say, well, it's not really white. You know, it just doesn't look real white. Okay, the projectors are imperfect. They're not equal distances to the board or the screen. Some of them have older bulbs, which are yellowy and bright and getting dim a little bit. But if you tell me that this white paper is not looking pretty damn white when I hold it up in the place where all three colors, red, green, and blue, are coalescing, you and I are not going to agree. I'd like to show you one more thing that I think is kind of interesting. I bought some fruits. I have a lemon, I have an apple, and I have a zucchini. It's a really deep green zucchini. And I'd like to talk to you briefly about this idea about pigments. The red apple appears red because of pigments, chemical structures that absorb certain colors and reflect certain colors. If I put it in white light, it appears red because the pigments absorb the blue, don't reflect blue. They absorb the green. They don't allow green to be sent back to your eye. This red apple only reflects red light. So if I put it in singular color, but that color is red, make a prediction. What color do you think the apple is going to appear? Red apples can reflect red. That's why they look red. So when put in red light, it's red. If we put it only in green light, it's black. That's crazy. Same apple, I assure you. I'm not playing a trick on you. But in only green light, it appears black, and if I get rid of any ambient other light in the room, it really appears black because, again, it absorbs green. It doesn't reflect green. The same should be held true if I put it only in blue light. If we take the zucchini and we put it in green light, it's dark, but it's green. Doesn't really disappear relative to my hand, the way the apple did. If we put it, the green zucchini in red light only, or blue light only, it really does appear black. And in red, similarly so, black. I'll start out with white light. And of course the lemon appears yellow, as lemons do, in white light. But again, what is yellow? Yellow is your brain's perception of simultaneously receiving red light and green light together. That's what yellow is to you. So it's a secondary color, yellow, as is magenta and cyan. Now, I can make yellow again, we saw that a moment ago, by combining green and red light. Now, if I put it in yellow, again, it's yellow, but if I put it in red light only, and yellow pigments can reflect red and green, but I only give it red light to reflect, it's red. Because there's no green. It could reflect green, but there is no green light present for it to reflect. If I put it in only green light, it appears green. And if I put it in blue light, well, it appears black. Now, if you were a careful viewer, you might have caught a little sleight of hand. I colored this, first of all, I chose the darkest lemon I could get. And I colored half of it black. Now, why did I do that? Well, I did that because the skin on a lemon is actually very, very thin. And so the pigments that make it appear yellow are really laid on top of white. You know, when you zest a lemon, it very quickly goes from yellow to white underneath it. And because there's that white truly underneath it, even in blue light, it still has a yellowish tint. Really, so I tricked you and made it black. In the interest of keeping it short, I just wanted to show you this color mixing, because again, you're doing problems where they say such and such appears yellow because of the removal of blue light, or the film appears magenta because of the removal of green light. And I wanted you to realize that green taken away from white light is magenta. Blue and red together, which are left over when you remove green, we call magenta. Because maybe this will help you understand why it drives me crazy when I hear yellow and blue make green. Okay, just like Jif and toilets going different directions in the hemispheres. Anyway, my set of gels actually comes with secondary colors as well. This is the amber, it's called, but it's yellow gel. So if I put it on the projector, and I'm using these cardboard frames just to choke out any white light that would come over the perimeter of the gel. So there's pure yellow. And I've moved this other, this is blue over here. Now, I kind of switched and that was red a minute ago. Now, if your art folks are right, when I turn on the yellow and put the blue on together, it should be green, right? But of course it's white. It's not green. Why is it white? Because this is light, and yellow light is red and green already. Add blue to it, and what do we have? Red, green, and blue, the primary colors which add up to white. Thanks for watching, and I'll see you down the road.